Okay. Okay. Welcome back, students. Welcome back, students. Welcome to the lecture series on signals and systems. In this lecture, we are going to deal with problems on periodicity and periodic signals related to discrete time. Okay, we shall concentrate on discrete time signals. Therefore, so now we shall start with this problem in showing that a complex exponential signal sequence like x of n is equal to e power j omega naught n, which is discrete time in nature, is now periodic only if omega naught 2 pi is a rational number. Given x of n is equal to e power j omega naught n, therefore, in order to check whether x of n is periodic or not, we need to follow the condition and check whether this condition is satisfied or not. Therefore, in order to verify this, I substitute the value of e power j omega naught n, that is the signal, and similarly with respect to x of n plus n, this signal now can be written as e power j omega naught of n plus capital N. And this can be written as e power j omega naught n is equal to e power j omega naught n into e power j omega naught capital N. This equation will be only satisfied if and only if this e power j omega naught n capital N is equal to 1. Okay. Therefore, in order to satisfy this particular equation, this value should be equal to 1. That is what I have. And based upon this will be only true only when that omega naught n value will be equal to some integer multiple of 2 pi. Okay, it is also possible for 0, but however, our fundamental period n can't be 0. Therefore, for all positive integer values of k, generally for all multiples of 2 pi, you will be able to see that e power j 2 pi k will be equal to 1. Therefore, now I could write that from this particular expression, I can generally write omega naught by 2 pi is equal to k by n. Here, k is a positive integer and n the fundamental period of the signal, which is also a positive integer. Therefore, it is a ratio of positive integers. Therefore, I can say that omega naught by 2 pi represents a rational number. And this is what we are asked to prove, and we have clearly shown that. Okay, I hope that now complex exponential sequence x of n is equal to e power j omega naught n can be considered periodic signal if and if your omega naught by 2 pi is a rational number. Similarly, we shall discuss another problem where I would like to obtain the condition for a discrete time sinusoidal signal to be periodic. Okay, in case of the continuous time sinusoids, we have already shown that all sinusoidal signals are periodic. But in discrete time case, not all sinusoid sequences are periodic. Okay, you need to remember this point, that all sinusoidal sequences, discrete time sinusoidal sequences, are not periodic. Okay, therefore, let us consider something like x of n is equal to a sine omega naught n plus theta. Okay, here a represents the amplitude. Okay, omega naught represents the angular frequency, n represents time, and theta represents a phase. Okay, n is the discrete time and omega naught is your angular frequency. And now a discrete time signal is periodic if and only if x of n is equal to x of n plus capital N. This is what we know, the condition to check whether a particular signal is periodic or not, and this should be true for all values of small n. Therefore, now considering x of n plus n, this will be equal to a sine omega naught into n plus n plus theta. And this can be written as a sine omega naught n. Okay, I'm just trying to expand this. Therefore, I get it as omega naught capital N plus theta. And this particular x of n plus n will be equal to x of n if and only if your omega naught capital N, that is this particular value, should be either equal to 0 or this should be equal to a multiple of 2 pi. Okay, because if it is 0, your n can't be 0 because it is a fundamental frequency. Therefore, it should be a value of it should be a value, and it is represented by the multiples of 2 pi. That is, there must be an integer m such that now your m such that omega naught should be equal to 2 pi m by capital N, or this can be written as 2 pi times of m by n value. Okay, or this can also be written as n is equal to, that is the fundamental frequency can be directly written as 2 pi times m by omega naught. From this equation, it says that for the discrete time signal to be periodic, the fundamental frequency omega naught should be a rational multiple of 2 pi, because you know that m by n is a rational number, and therefore omega naught should be a rational multiple of 2 pi in order to have your discrete time sinusoidal signal to be periodic. Otherwise, the discrete time signal will be a periodic. And the smallest value of this capital N, okay, the smallest value of this positive integer capital N for some integer small m, for some small integer small m, it is known as the fundamental period. I hope that it is clear. And now let us proceed further in order to deal with some problems on discrete time sinusoids, and we shall check whether that signals are periodic or not, and if they are periodic, let us also find out the fundamental periods of those signals. Okay, I shall start with a signal like cos 4n. Given that x of n is equal to cos 4n, let us consider this as an example 1. Okay, where we were given x of n is equal to cos 4n, and we were asked to check whether it is periodic or not, and if periodic, we should also find out the fundamental period of this signal. Okay, you could see that this can be written as, this cos 4n can be simply written and compared with the usual nature of your cosinusoidal signal, which can be written as cos 2 pi fn. Here clearly, so upon comparison, I can find it out that 2 pi f, that is omega naught value, is equal to 4, and from this I can now write my frequency value f as 2 by pi. Okay, that becomes generally f becomes 4 by 2 pi, and upon cancellation I get it as 2 by pi. Since your f is not a rational number, because we know that pi is an irrational number, since f is equal to 2 by pi is not a rational number, okay, therefore f is not rational. Therefore, you can also say that x of n is not periodic. Okay, it is a non-periodic signal. Okay, this is how you need to check whether a particular given signal is either periodic or not. Okay, and we shall proceed further in order to find out one more example where I consider a composite signal. Example 2, where I consider a composite signal like x of n, which is a sum of two discrete time signals like sine 2 pi by 2 pi n by 3 plus cos 2 pi n by 5. I consider a composite signal like x of n, which is represented by the sum of two sinusoidal signals. And now I would like to compare this with x of n is equal to sine 2 pi f1 n plus cos 2 pi f2 n. Okay, we shall individually find out the frequencies and check whether they are representing with rational numbers or not. And if they are representing with rational numbers, let us also find out the individual fundamental periods. For the first signal like sine 2 pi 3 by n, I could find out upon comparison with this, I could find that 2 pi f1 is equal to 2 pi by 3, or you can also say that f1 is equal to, okay, upon cancellation of 2 and 2, pi and pi on both sides, I could see that f1 is equal to 1 by 3, which is equal to some k by n. Okay, which is represent, okay, let us name it as k1 by n1. That is, it is representing a rational number with respect to sine 2 pi 3 by n, 2 pi n by 3. And similarly, we shall also compare the second signal and check that 2 pi f2 is equal to 2 pi by 5, and it says that f2 is equal to 1 by 5. And here also, now it is representing a rational number, and therefore these two signals, discrete time sinusoids, are periodic in nature. And now let us find out their fundamental periods too. Okay, in this case, upon implication, you can clearly see that n1 is equal to 3, and here from this you could also see that n2 is equal to 5. Okay, and they represent the fundamental periods of the signal. And now, however, I would like to check whether this x of n is periodic or not. I need not check whether they are individual. However, so in order to find x of n is periodic or not, we need to find out their individual fundamental periods. And therefore, upon finding, now I would like to find out the ratio of n1 by n2 to check whether x of n is periodic or not. And you could find here n1 by n2 is equal to 3 by 5, which is the ratio of two integers, and therefore the sequence x of n is periodic. And this periodic signal and x of n has some periodicity, which can be calculated as the LCM of n1 comma n2. We have actually seen this rule with respect to continuous time signals, and this is also applicable here. Therefore, here the LCM of 3 comma 5 is given by 15. Therefore, the given sequence, that is the sum of both x1 of n and x2 of n, is also periodic with a fundamental period of n is equal to 15. This is how we can check whether a composite signal is a composite discrete time signal is periodic or not. And similarly, so I shall finish off this with another problem, example 3, where I consider some exponential signal like e power j into pi by 2 into n. Okay, I would like to check whether this signal is periodic or not. Therefore, upon comparison with e power j omega naught n, I could find that my omega naught, or 2 pi f in this case, is equal to pi by 2. Therefore, upon cancellation, I find that f is equal to 1 by 4, and which is also representing a rational number. Okay, and here, therefore, your x of n is equal to e power j pi by 2 n is also periodic with a fundamental period of n is equal to 4. Okay, I hope that you are able to understand how I have written this fundamental period, as well as how I have checked that whether the discrete time signals are periodic or not. Thank you. That's all for this lecture.